porque suelo ser un poco nervioso, entonces... Hay menos noise. Sí. Mira, aquí... Chullos para hacer que para hacer diapositivas por partes, me hace cosas y algo. Lo he practicado antes y tardo 38 minutos. Sin querer, pero más o menos creo que sí que durará lo mismo. Vale.
Today we have Miguel A, who is going to talk about the Kondo systems. He is a PhD here since 3 years ago. I guess he did also the master here, and now he's in the last year of his PhD. So, thank you.
Thank you. Well, hopefully. Let's works about my both of them related with my PhD thesis, but anyway, at least well, everything is connected at the end. Yeah. Yeah. Yes. But okay. With David and Rosa from this institute, and this about okay. The outline of this first part, it seems too much, but it's not. First, I will give a small introduction. I will talk about what is a quantum dot. I will explain what is the Coulomb Locate effect, and then I will explain the concept why it's important in nanostructures. Then I will present 3 models to explain the Kondo effect, but all of them tries to explain the same. So it will be quick, and at the end I will extract some conclusions. Well, first, quantum dots. What is a quantum dot? A quantum dot is a region in space where electrons are trapped. It's like locking people in a room, but instead of people in a room, it's electrons in metals. How do we do that? First, we create a 2-dimensional electron gas. What we do is we put different materials, and in the middle of these 2 materials, sometimes can be created a 2-dimensional electron gas. Electron gas, if we create gates above, we create like walls where electrons cannot go through. With this, we can create a small region where electrons can be trapped in a small time. With another electrode, we can modify how the quantum dot is shaped. So we can control the energy levels of the quantum dot. And it's not totally closed, so it permits transport between one part from the other. So there is tunnel coupling between the quantum dot and the oxide and the 2-dimensional electron gas. Okay, quantum dots can be done in different ways, but semiconductor quantum dots is more or less what we are going to work on it right now.
But do you know that there is no 2-dimensional quantum? You know about this?
What?
There is a bit high quantum dot.
A bit. A width. Ah, yeah.
Speaking is not 2D.
Yeah, no, it's a small region at the end. It's not 0-dimensional, of course.
But simply for you, for future, there is a so-called lateral quantum dot and vertical quantum dot. The because vertical quantum dot is different than lateral.
Yeah,
Which you
of course.
talked about, probably.
Yeah, no, I know. Yeah.
Therefore, you should tell people about it.
Yeah. Well, I'm going only to explain this type of quantum dot. Okay. Coulomb Locate. We know that well, the quantum dot normally usually is small. So since it is small, electron-electron interactions are important in this system, and due to that, it occurs the Coulomb Locate. What is, we create a voltage bias, an electron can go from one side to the other, and if we put the opposite potential in the other way. Okay. If instead of that we have one electron, we know that electron-electron interactions are important. So due to that, the electron cannot go through one part from the other, because some kind of energy has to be overcome in order to go through this system, and an additional resonance is created, which is located at the energy level plus this charging energy potential. Okay. Experimentally, we can find it in the electrical conductance. If we have one level, the Coulomb Locate is signature is different resonances, but located at different positions that are the energy level plus the Coulomb Locate energy. Additionally, if we plot the voltage where transport is not permitted, these are called Coulomb diamonds, and is another signature of Coulomb Locate. Okay, this is Coulomb Locate. Kondo Effect. Kondo Effect is a effect that is known from more than 100 years, and was first found in metals with magnetic impurities. But nowadays you can see, we can simulate it with an electron reservoir and a quantum dot. We know that a metal or electron reservoirs has plenty of electrons, and the impurity can be one energy level and one electron or two, but right now we only care about one. Each electron has spin, and the impurity of the quantum dot is coupled with the electron reservoir, so the energy level interacts with the spins, and with that we create a singlet in the impurity, which is a combination of up and down of the spin. This is in the resistance or in the conductance. In the resistance, we know that the resistance, as we are lowering the temperature, the resistance also goes down, decreases. But what the Kondo Effect does is that at a characteristic temperature, which is the Kondo temperature, the resistance reaches a minimum and then increases again, which this is not common in normal metals. Additionally, in the conductance, the conductance near the Kondo Effect takes a logarithmic scale. I have to remark that if we still lowering the temperature at really low temperatures, this diverges. Eh? What is the relation of magnetic impurities? Is because due to magnetic impurities, a level is created, and we have this interaction with the spins. We need that. We need that.
No, it's not true what you said. We confuse people. Because the question is, do you need a magnetic field for this or not?
No, it's not needed.
Then why you talk about magnetic impurities?
Because you need that the spin is important here.
Yes, spin important always, but what you talk about? You talk about Zeeman effect or you talk about something different?
It's something different. This is an interaction of a spin with the whole system. With the spin of the whole system. It has to do, it has something to do with the magnetic impurities.
So for you, the Kondo effect is the creation of a singlet state.
It's a creation of a singlet state.
The
Yeah,
Kondo is the creation of a singlet state.
a singlet
What
state.
is caused by magnetic impurities caused by the quantum dot is not relevant.
The problem here is the magnetic impurity is due to this change of spin, because the spin is changing all the time.
So the electrons in the metal are spinning the impurity.
Yeah.
The spin of the impurity.
Yeah.
So there is a effective antiferromagnetic
What is the
interaction.
impurity? What is the impurity?
This is the impurity.
The quantum dot is the impurity.
The quantum dot is the impurity in this case. Yeah.
Because you call it a phenomenon, but unfortunately, it's not a good example how to try to use it. But anyway,
I think that the original Kondo effect is for impurities.
It's for impurities.
Yeah.
This was the original one.
Yeah. This is the artificial.
A similar effect.
Similar.
Consider the quantum dot as
As impurity. Yes.
simply for you advice, if you want to defend this, better if you talk about quantum dot, you should not only talk about Coulomb Locate, because you have shell effect. For example, you demonstrate picture, which is Tarucci experiment, which shows that not only Coulomb Locate playing important role, but shell effect, quantum effect, which is missing in your picture. It's simply advice for you in future, okay?
But this is what I care right now. Of course, there are lots of many effects.
People a little bit. You have to be very transparent. Then it will be clear what you talk about. You understand? Simply advice. Simply, friendly advice.
Fermi energy. And this peak, it has a narrowing of more or less of the Kondo temperature. This occurs only at temperatures lower than this characteristic Kondo temperature. If not, this Kondo peak disappears. Okay, this is the Kondo effect. Thermoelectrics. Well, we know that if we put a battery in a metal, and electric current is induced. So, and additionally, if we hit a stream of a metal, a heat current occurs in the metal. But we also have some kind of cross phenomena. A thermal bias also induces electric current. If we hit one stream of a circuit with different metals, a current can occur. And with this, we have thermoelectric conductance of this. And with this, we have the electron thermal conductance. This is known for years and years, but right now the interest has increased because it seems that lowering the dimensionality of the system enhances the thermoelectric properties. So right now it's a subject, interesting subject to know. It's good to know thermoelectrics in nanostructures. Okay, let's go to the system. First, I'm going to take the perturbative approach. With this, what we have is the Hamiltonian, which represents hoppings from one reservoir to the other, interacting with the impurity with the spin. This spin hopping amplitude is dependent of the parameters of the quantum dot, and is the term we are going to use to do the perturbative expansion. The perturbative expansion, we do it in the electrical current in order to find the conductance. after long of calculations, we have this conductance. Has two different parts: the regular cotunneling, which we don't care so much, and the change cotunneling. In order to find the Kondo temperature, which is the characteristic scale of the Kondo effect, what we see is when this 1 minus this term is inverted. Is inverted in sign because the model is not valid at the end after this.
Yes, or it's something different. Before you have
What?
transparency. Before. Yes, you have time dependence, right?
Yeah.
So
We have implemented integrals in time, and we went to the Fourier space. That's why we don't have here any time dependence at all, and we are taking into account only in the Kondo resonance. So we don't care about all the other parts of the system. Only the Kondo resonance.
Steady state or static solution, or what is it?
It's the Fourier transform. So at the end, it's an integral over time.
You integrate it over time.
Yeah. Okay. And we find is a Kondo temperature which is dependent of theta, which depends on the intrinsic Kondo temperature, which is the temperature at theta equals 0. And it has this shape. At first, we have a Kondo regime where the Kondo effect prevails. Kondo quench when at the end it disappears totally, the Kondo effect. Okay, this is one model. We have seen what is done. At the end, at large thermal biases, we hit one reservoir maintaining the other cold. The Kondo effect disappears.
What was theta?
Theta is the difference of temperature between one reservoir and the other. Okay, we go to another model with it's another Hamiltonian, but it represents almost the same. We have a dot Hamiltonian, an interaction between the dot and the reservoirs, and the lead Hamiltonian, which are the electrons in the reservoirs. And then with this model, is the slave boson theory, we need a Hamiltonian that ensures that the quantum dot is only occupied with one electron. That's why this term of the Hamiltonian, temperatures. Okay, with this we need to solve two equations. This is first, these operators are operators that create states in the vacuum. So we need to establish that is steady at long times, and we have the Lagrange conditions that ensures that the quantum dot is only single occupied. There is only one electron in the quantum dot. With this, we arrive to this integral that seems quite complicated, but we have a function that it depends on the Fermi distribution function of the leads. The broadening is how the width of the resonances of the system, and we have gamma tilde and epsilon tilde, which these are the important parameters because one is the Kondo resonance width, the Kondo resonance, how narrow it is, and the Kondo resonance position, where is the Kondo. On this, the width is related with the Kondo temperature. So we are going to study more on this. We find is that the Kondo splits in two different resonances. But basically, that's what that's what we find. Additionally, the width decreases. This is a kind of dephasing. of the Kondo resonance. But what is interesting is the temperature bias. In the temperature bias, what we find is that at first the width doesn't change, then start to decrease, and then it disappears. This is practically the same as the last perturbation theory we did before. So both models more or less agree, even outside the range of validity of these two models. So we can be more or less sure about this system. Okay, right now the problem is that we cannot say too much about the transport. That's why the other one, but the good thing of this Hamiltonian is that you can obtain the other ones with this one. Okay, we have the lead Hamiltonian, which are the electrons of the reservoir, the tunnel Hamiltonian, which is the hopping between the electrons here and the quantum dot, and the dot Hamiltonian, which is the energy level of the quantum dot and the electron-electron interactions. With this, we try to compute the electric current. The electric current is defined with as the evolution of the occupation in one of the reservoirs. We have chosen the left one, but anyway, the sum of both is equal to 0 due to Kirchhoff. And applying the Green's function formalism, which I'm not going to show the details, we find this expression, which depends on of the difference between the Kondo of the quantum dot, and this transmission, it depends on one function which is called retarded Green's function. I'm not going to show the solution of the retarded Green's function because it's complicated and is not of total interest. Is more interesting the results of it, but I want to remark that we have a self-consistent calculation. The retarded Green's function depends on itself. Okay. First, I want to show the spectral function. The spectral function is defined like that. It's the imaginary part of the Green's function, but at the end, what we find is three different peaks. One is the energy level peak, the energy level resonance. The second one is additionally we have compute what are the voltage effects and the thermal bias effects. The voltage effects one of the voltage effects is a splitting of the Kondo peak as expected, but we don't find dephasing. The peaks doesn't destroy it at large voltages. This is a drawback of the model, but anyway, qualitatively is what we expect. And the thermal bias effects, we have a smoothing of the Kondo resonance, a large thermal bias, but we don't have the Kondo quench that I have shown before. For the same reason, we don't have dephasing. Okay, let's go to the transport. With the voltage, at 0 voltage in the electrical conductance. This is a signature of the Kondo effect, basically. And then we have the temperature bias effects. We have find strong nonlinear behavior in the thermocurrent, but also in the thermovoltage, even with two non-trivial zeros. Well, in previous works we have shown that we can find one non-trivial zero, but the good thing is that the difference is that the Kondo peak can induce another one. In order to explain how these non-trivial zeros are created, can be done with three different energy diagrams. When we have a little small thermal bias, we have only a little window where transport is permitted, and this window is in the Kondo peak. The Kondo peak is slight above the Fermi energy, So electrons will go from this side to this side, making this current positive. If we increase the thermal bias, the window opens, and then we have the energy level of the system, which is below the Fermi energy, and then we have a negative electrical conductance, thermoelectrical current. And with this, we have explained the shape of this strange curve. Okay, as a conclusion of this work, we have implemented three different approaches. We have demonstrated that with the perturbative approach that the Kondo effect vanishes at large thermal gradients. We have demonstrated the same with the lazy boson-Millfield field theory, and additionally we have shown that the Kondo peak splits at the increasing voltage. And with the non-equilibrium gauge function method, we have shown the zero bias anomaly, and we have found nonlinear thermoelectric transport. Okay, this is the first work. I have another one. Alvar Garrigues, Enrique del Vargo Legia, and Christian Nihuis from Singapore, Ningbo, and Florida universities, and this is about interactions and temperature dependence in molecular junctions. Okay, before I have talked about the outline is a small introduction as before. The model, which is the same model as I explained before, is going to be quick this, and then I will explain how to distinguish between interacting and non-interacting cases. Okay, before I have explained the quantum dot. Right now, the only difference of a molecular junction is that the quantum dot is substituted by a molecule. The molecule can be modified by the gate voltage, but at the end it's the same system, more or less. I want to explain more or less. We have two triangular shapes of metals, and these two triangles are connected in a small region in one of the vertices. If we increase the voltage between these two sides, this point breaks, and there is no transport between them. And after that, we have a hole here that, if we are lucky, after put a solution in water, if we are really lucky, a molecule puts in this gap, and we have a molecular junction. This is how it is created, and this is called electromigration. Okay. First, I have to talk about a previous work that one of my collaborators did. What they found is that in a molecular junction, they studied the temperature dependence of peaks depending on the gate voltage. This is the energy level of the system, and with this, in different points of this system, they find that increasing the temperature or some of them decreases, some of them increases, and others are more or less the same. They implemented, in order to explain that, Landauer formalism, some kind of model, but non-interactive model, I have to say. And with this, they try to fit the results, the experiment. As I have explained before, we can have Coulomb Locate effects. Interactions can be important in the nanoscale. That's why, and also in this is the conductance between applied voltage and gate voltage, and it seems that there is some kind of diamond shape. So an open question is, can we explain the same experiment using an interactive model? And that's my work. The Hamiltonian I'm going to explain, I'm going to do that now, is the same Hamiltonian as the last one I have shown. The only difference is that the energy level is now the one molecular energy level. Okay, this is the Hamiltonian. This is two leads, the molecule with Coulomb interactions and tunnel between the molecule and the leads. We compute the electrical current. Well, before I said that I'm not going to explain how we obtain the Green's function, but this is easier to obtain. So I'm going to explain quickly what we obtain. The Green's function is some kind of correlator in this form, and what we do is we evolve in time this correlator. Using this, we go to the Hartree-Fock solution.
Yes, one question. In the current expression, there is no the lesser Green function that appears when the tunneling barriers are not proportional.
If you modify everything, you can obtain this result. Yeah.
No, you need to have the gammas to be proportional and energy independent.
Yeah, but we're talking about one interacting model. Well, only one level.
Yeah, independently of that.
In one level, everything is proportional.
In one level,
The gammas are always proportional because the gammas are scalars.
yeah, but they could have some energy independence.
We can talk later, but I can sure that this can be done in this way. We have done it. It's one interacting model.
Yeah, okay. Later we can discuss.
Okay.
Very naive questions and answers simply.
Yeah.
If you have one electron, how you have interaction?
No, we can. We let both spins to interact. So the electrons with different spins can interact. Electrons in the same level with different spins can be in the same energy level. So these both electrons can interact.
You always consider singlet state, right?
No, in this case there is no singlet state.
But,
Yeah, well, there is one energy level, and we permit to be one or two electrons.
this is a different spin orientation.
There is a
This different spin orientation.
spinner.
Our principle.
Spin oriented.
Yes, our principle allow only a different spin orientation. Yes.
We let different spin orientation. Yeah.
And otherwise, we violate our.
Mm-hmm.
What changes if you consider other molecules, the value of epsilon n?
Yeah. At the end is how we modify this.
And the energy.
The energy level. This is the only thing. We fit the properties of the energy level, and then we see what happens. Okay, and we obtained two different resonances. One, both of resonances are which is related of the hybridization energies. Okay, this is just the width. And I have to remark again that this is a self-consistent calculation because this depends on the occupation number and the occupation number depends on the Green's function. So we have a self-consistent calculation. And what we find is, okay, in the current versus voltage, we have, okay, we can fit both peaks. And we have a good agreement with experiments, even large thermals, large temperatures, and we have the Coulomb Locate Coulomb diamonds. If we plot the voltage gate versus voltage bias, and if we compute the current versus temperature as comparison, this is the non-interacting model. Both peaks, they have these both peaks in the electric conductance, and this the thermal effects, some decreasing behavior and some of them increasing. With our work, we have more or less the same, the two peaks, and in different points, we have fitted with, and we have more or less the same result. So how we can we distinguish between these two models? That's the question, because both of them are practically seem practically the same at the end.
How large is U here?
U maybe 80 millielectron volts, or I don't remember so much, but later I can check and I tell you.
Because if U is very small, then both should be similar.
Both are similar, but can we distinguish them?
Mention U.
We can apply a magnetic field in some B, and depending on the change of spin between one level and the next one, the resonance will move in one side or in the other side. Yeah. So if we have an interacting model, what we find is one level will go to the right and the other level to the left, and other peaks will do the same. But if we have a non-interacting model, what we find is that the Zeeman is the Zeeman effect. A level will split in two. So with this method, we can detect between an interacting and non-interacting model case. Yeah, no, but we have to say it. We have to prove in some sense. It seems quite trivial, but yeah, but this is the shift. This is U. So the U is more or less the same order of the label spacing.
So U is very small.
Well, it's a molecule. No.
So then it's somehow expected that both models, non-interacting and interacting, can give you similar results.
Yeah,
because
of course.
U is very small.
Exactly.
Okay.
Yeah. That's the reason why we're doing this work.
Okay.
And well, they did an experiment, and they compute with one molecule at very low temperatures the electrical conductance. We have found two resonances. There are some experimental problems that the spin is not always 1/2, so we can find different resonances moving in the same way. Also, if the temperature is a little bit higher, it's really difficult to distinguish interacting and non-interacting cases. And well, molecules are very complex at the end because they have orientation. They can put in the junction in different ways. We never know. Okay, so at the end, we have seen previously they have done an experiment with a molecule, and they have found some temperature effects that can be explained with a non-interacting model. In our work, we have done an interacting model that also, if it splits, we have a non-interacting case, and if only separates or if it or gets closer, we have an interacting case. And there are experiments that more or less show that the interacting case can happen. And with this, that's everything. Thank you, everybody, for your attention.
Now, time for more questions.
On your first work about this Kondo quench with the temperature bias, is there some experimental evidence of this?
With thermal gradients, not yet. We know that on total background, thermal background destroys the Kondo peak, but with a thermal bias, we don't know yet experimentally.
And you emphasize this thermal bias, but is there also the dependence on the average temperature?
Yeah, of course.
Besides the
But
usual-
we try to get the bias, the background temperature low. At the end, we need a low background temperature because if not, we don't have Kondo effect.
But besides this expected dependence on the temperature, are there additional behavior?
No, so you have a cold reservoir and hot reservoir. What we have found is that despite we have a cold reservoir, the Kondo peak disappears, which is not the same as all the temperature increasing, you know?
No, then let us thank